Okay, I'm printing out some stuff here. Should be done soon. Let's see. I think I got homework posted for this class last weekend, I hope, or sometime. This one I seem to have mostly under control. I've had a string of disasters in my other two classes, but this one we're doing okay on. Oh, these came out odd. Oh well. More with momentum today. So, and we'll start looking at collisions, I think. And I think most of the problems that we'll be looking at here, I pulled out of the textbook. I'm not positive about that, but they sort of look like it. So they're at about the same level. And let's hop over to the pivo thing. So I can minimize that. So have that. The first one is an example of basically a collision in reverse. And this is something that, I don't know if any of you are hunters or not, but something that you very much want to do is, if you're shooting a rifle or a shotgun, hold it snugly against your shoulder, because momentum is conserved on those things. And if a bullet comes out of the rifle, or the whatever it is comes out of the shotgun, there's initially no momentum in the shotgun rifle system, or the shotgun bullet system, or the rifle bullet system anyway. And if some momentum ends up going to the right, there's going to be some momentum to the left, and equal amount of momentum. And so that's the recoil of the rifle, and it's a matter of conservation of momentum. And if it's not held snugly against you, then it can slap against you and kind of hurt. So got to watch out with that stuff. So we'll imagine a 7-kilogram rifle used to fire a 10-gram bullet, which is traveling at a speed of 700 meters per second. What's going to be the speed of recoil of the rifle? Okay, well, this is going to tax my drawing skills absolutely to the limit, but here's what we have initially. We've got the rifle here, and the bullet is inside of it. So that'll be the case. And then there's no momentum. So we can say that P initial is equal to 0. Now the bullet and the rifle comprise our system in this case. And in the absence of external forces, or before they get a chance to do anything, now in the absence of external forces could mean that the hunter is holding the rifle loosely and not in contact with his shoulder. So that could be the situation that we have. But in the absence of external forces, the momentum of a system will remain constant. So after the bullet is fired, now the hard part is, can I draw that thing more or less the same? Well, the length is about the same. It just doesn't have a bullet in it this time. So you've got the bullet that is taking off here, and this would be P for the bullet in that direction. The rifle is going to be recoiling in that direction, so we'll have a P for the rifle in that direction, and the sum of these two has to add to 0. So we would have P for the rifle plus P for the bullet are going to also equal 0. And that's P final. So P final will equal P initial. Okay, well, I can say, if I say positive is to the right, I could say that the bullet's going to have positive momentum. So we'll have the mass of the bullet times the speed of the bullet. The rifle's going to the left, so it'll have negative momentum. So I'll have minus the mass of the rifle and the speed of the rifle. And those two things equal 0. So we end up with the mass of the bullet, the speed of the bullet, is equal to the mass of the rifle and the speed of the rifle. And the speed of the rifle will end up equaling VR equals mass of the bullet, V for the bullet, over the mass of the rifle. Okay, so it's going to be a fraction of the speed of the bullet, which is a really good thing. You wouldn't want to get hit with a rifle that was going at 700 meters per second. But we'll just see what we come up with for a number here. Mass of the bullet was 10 grams. Now, that is, well, I can just write it as 10 grams, actually. And the speed of it is 700 meters per second. Most of the time, we deal with purely kilograms. But for that mass of the rifle, I'm going to take that 7 kilograms and replace the K with times 10 to the third grams. All of our units, like the Newton and the watt and everything like that, are written assuming you are using kilograms. But for this thing, we're taking a ratio of masses. So it's okay to replace that kilo with 10 to the third in this case. So we would actually, I think we get about 1 meter per second on this thing, because 700 times 10 is 7,000, and that's 7,000. Yeah, we just get 1 meter per second is all it happens to be. So could have done that without writing stuff down, although I would not have trusted myself to figure it out correctly without writing it down. B asks, how much energy does it transmit to the shoulder of the person using the rifle as it stops? Well, the rifle is going to have a kinetic energy of this much. Its energy, kinetic energy, is going to be 1/2 the mass of the rifle times the speed of the rifle squared, which is going to be 1/2 times 7 kilograms times 1 meter per second squared, which I think comes out to 3.5. It'll be kilogram meter squared per second squared, which are joules, and 1/2 times 7 times 1 squared, but 1 squared is just 1. So it's going to be 3.5 joules is how much kinetic energy it'll transmit to the shoulder of the person using the rifle as it stops. Okay, this would be if you dropped a 350 gram object 1 meter. I'm trying to think what 350 grams would be like. That'd be about I think it's around the weight or the mass of a can of pop, but I'm not sure. Yeah, I'm just not sure about that. Let's see. Oh, I know how. It'd be 0.35 kilograms. On Earth, it would have a weight of about 0.8 of a pound. So imagine something, or just imagine taking 3 cubes of butter and wrapping them together with, and make it frozen butter. Let's see, wrapping them together with a rubber band so they're all one chunk and dropping it 1 meter, which is a little over 3 feet, and having it land on your foot. That might hurt a little bit, but it wouldn't hurt tremendously. So this isn't too bad of a problem, I think. By the way, this does ignore something. It only looks at the rifle and the bullet that's heading out of it. The rifle actually acquires a bit more recoil than that because the bullet isn't the only thing that comes out of the barrel heading in that direction. There are also the propellant gases, which when you fire a bullet, there's this stuff that explodes and expands. that also comes out of the rifle and carries a bit of momentum with it, but the bullet gets most of it. And so, but that'll add to the recoil of the rifle a little bit. So anyway, there's our first, this is a collision in reverse, in effect, is what it is. And here's another one. This is a situation where you start with no momentum and end up with some. So we'll have two blocks, masses m and 3m, placed on a horizontal frictionless surface. So this could be like an air hockey table. Maybe you've got one air hockey disc just by itself, and then you take 3 air hockey discs and stack them together and glue them somehow. And then you put a light spring attached to one of them, and the blocks are pushed together with the spring between them. And when we say light, that's code for massless. You can ignore the mass of the spring. So that's what we'll have here. But this is 2 blocks on a frictionless tabletop, so we'll go with that. And something like that. And then there's this light spring. And some external agent like you is pushing them together. And then what you're going to do is just pull your both hands away rapidly so that the spring is free to push those things apart. And so P initial in this case is going to be 0. They're just sitting there being held together by you, and the spring is pushing mightily to try and separate them. And we'll imagine that after they're released, we'll have one of the things heading in this direction with a speed v3, and the other thing heading in this direction with a speed, a speed v1. Okay. And so that's what we have, and P final is equal to 0. Okay. You had no momentum before the collision, you'll have no momentum before the separation, that is. You'll have none after the separation either, which means the momentum of this one, which is going to be 3m times v3, minus this one's going to be m times v1. Those combine to give you 0. Okay, the block of mass 3m moves to the right with a speed of 2 meters per second. What's the speed of the block of mass m? Well, intuitively, you could just about figure this out, but let's go ahead and solve for v1. And if I kick this term across, I'll get 3mv3 is equal to mv1. I can divide both sides by m because one of the blocks is m and the other one's 3m. So I just divide the m's out, and I'll get that the block of that lighter mass, or the speed of that block, lighter block, is actually going to be 3 times the speed of the other one. And we know the speed of the mass 3m is 2 meters per second. 3 times that is going to be 6 meters per second. The smaller mass moves faster when you have this kind of a situation going on. So there's another collision in reverse. So we're using momentum to solve some things that we just didn't really have access to before. We would have had to take the intermediate step of somehow analyzing using Newton's third law throughout the collision, but instead we can just use this momentum stuff. Now, this time's actually going to be an example of something called an inelastic collision. And in an inelastic collision, kinetic energy is lost, or mechanical energy is lost. And we have this arrow moving at 90 kilometers per hour, which isn't super fast, but it penetrates a block of wood suspended by a rope. What impulse is delivered to the block, and what velocity will the wood block acquire if its mass is 5 kilograms? Okay, it says it penetrates the block of wood. It's going to take energy for that arrow to drive into the block of wood, and so it will lose kinetic energy. But momentum is not lost, and so that's something that we have to know here. All right, well, here's the initial situation. We've got this arrow here headed along at 90 kilometers per hour, which are ridiculous units to give us for something like this. But I'll just replace the K with 10 to the third and 1 hour with 3.6, actually, this is what I can do, K seconds. 3,600 seconds is 3.6 K seconds. And now the hours will divide out. I've got a K here for kilo. I've got a K there for kilo, and those divide out, and I'll end up with 90 divided by 3.6 is maybe a round number. I don't know. Turn on calculator first. Oh, I need to get out of this mode. I was looking at lots of significant figures today. Okay, 25 meters per second is what that happens to be. So this thing's moving along here at 25 meters per second. This is actually a way of determining muzzle velocity. You'd have this thing attached to a rope that's attached to the ceiling. And if you film something like this carefully, if this was a bullet that was going into the block of wood instead, if you filmed this carefully, especially if you filmed it against a backdrop that showed degrees on it, if you figured out how far the thing swings up, the kinetic energy that's acquired by the bullet and the block, or that it has immediately after the collision, will turn into gravitational potential energy, and you can work backwards and figure out the speed of this block bullet combination. Then you can use that to figure out the speed of the incoming bullet. In this case, we've got an arrow, but it's a way of determining muzzle velocity anyway. And I don't know, there's probably some better way of doing so, but that's one way that would work at least. Okay, so we've got the block here. This is 5 kilograms. This is 25 grams moving at 25 meters per second. And we'll have P initial equals P final again. But in this case, the initial momentum is going to be our 25 gram arrow, which 25 grams times 1 kilogram over 10 to the third grams. If you figure that out, you'd get 0.025 kilograms. Dividing by 1,000 moves the decimal point 3 places to the left. So our initial momentum, 0.025 kilograms, is going to equal, whoops, times the speed, 25 meters per second, is going to equal our final momentum, which is going to be an arrow stuck inside the block. So it's going to be 0.025 kilograms plus 5.0 kilograms. We'll assume, bad assumption here, but that we have something like that. If I was to rewrite this problem, I think I just lifted it directly from the book. I would say 25.0 grams, 90.0 kilometers per hour, and 5.00 kilograms. And let's pretend I just do that. So 5.00 kilograms, 90.0 kilometers per hour, and 25.0 grams. Okay, now we'll have 3 sig figs, although in this case, not quite. But anyway, this would be times V final. Okay, we have a single object moving at the end. An arrow stuck in a block is moving with that block. So, and the impulse delivered to the block, well, we'll have to kind of figure that out. The impulse delivered to the block will be just the mass of the block times its final velocity. At first, we're going to figure out just the final velocity of the block. So V final will equal 0.025 kilograms divided by 5.025 kilograms. Whoops, and I've got my 25 meters per second on here. That poor thing, I keep forgetting it. Meters per second. Okay, so plug and chug, 0.025 times 25 divided by 5.025, and I get about 0.12. I guess I can keep 3 sig figs now that I've introduced them. This would be meters per second. The kilograms divide out, and I'm left with meters per second. Now, that's the momentum of the arrow-bullet combination, or that's the speed of the arrow-bullet combination. The first question asks, what impulse is delivered to the block? What did I say? It's the speed of the arrow-block combination. I hope I said that. Anyway, the impulse delivered to the block will just be the momentum of the block. And so part A, impulse delivered to the block, is going to equal the mass of the block times that V final. The arrow, it continues to move. It doesn't lose all of its initial momentum. It's not moving very fast because it was going 25 meters per second, and afterwards it's only going 0.124 meters per second, but it's not zero, so it doesn't lose all of its momentum. So the mass of the block was 5 kilograms, so 5 times that thing. And impulse equals change in momentum. I get 0.622 kilogram meters per second. So that's the impulse delivered to the block. And I don't know, it doesn't immediately occur to me how I could figure that out first before I have figured out this number. I guess I could have taken this expression and just multiplied it by the mass of the block, but that doesn't seem all that interesting to me. Okay. Talk a little bit about collisions here. Here we've got something like what we did yesterday, where we had we have a clay model of a koala bear has a mass of 0.200 kilograms. There's lots of incidental detail here. And it slides on ice at a speed of 0.750 meters per second. It runs into another clay model, which is initially motionless and has a mass of 0.350 kilograms. Both being soft clay, they naturally stick together. What is their final velocity? Okay, and it says they're on ice, which is code for frictionless surface. So their final velocity, the second one is initially motionless. I can't draw koala bears, so I'm going to draw squares instead. So initially we've got this thing moving along at 0.750 meters per second, and I'll call this thing M1 and this V1. So that's what we have for momentum. And then it strikes and sticks to this second mass here. So the momentum before, I'll just say initial, is going to equal final. So I'll have M1 V1 is what I have for initial momentum. Well, afterwards, I've got M1 and M2 stuck together as a single mass. So my final momentum is going to be M1 plus M2, and then V final, whatever that happens to be. So I didn't draw a picture of them stuck together after the collision, but that's the idea here. So V final will equal M1 V1 divided by M1 plus M2. Notice solving a problem like this, I'm not even mentioning Newton's third law, which is what this conservation of momentum depends on. I'm not mentioning Newton's second law, where we'd have forces and accelerations and things like that. I'm not sticking time into it because I don't know how long this collision lasts. All I know is momentum is conserved. And so I just figure out an expression for the initial momentum, figure out an expression for the final momentum, just reasoning through the thing, and set them equal to each other. And then solve for the quantity I want, which will be V final is going to equal M1, which is 0.200 kilograms, times V1, 0.750 meters per second. And I divide by the combined mass at the end. Well, 0.200 plus 0.350 is 0.550. And that's all I have to do. Plug in the numbers. 0.2 times 0.750, turn on calculator. 0.2 times 0.750 divided by 0.550. And it's not going very fast at the end. I get 0.273 meters per second. So there, that wasn't too terrible. Any questions on that one? Got a series of these problems. I want to tell you, this isn't one that I'm going to solve in here, but it's one that we do in the engineering physics class. This is as sort of a break from the calculation one. And what it involves is a gravitational boost that a spacecraft can get from a planet. And the gravitational boost we'll be interested in is one that was given to the Voyager spacecraft, and we'll imagine that Jupiter is going in this direction, and there's a little spacecraft that's coming toward it in this direction, and this is Voyager. And what happens is it has this encounter with Jupiter where Jupiter's gravity slings it around there, and it's got a V initial. This is the speed of Jupiter. And then the spacecraft will have a V final as well down here. So that's the effect that occurs in this case. And we analyze this situation both from, well, we have to use two tools, the conservation of energy and the conservation of momentum. And this is Voyager at Jupiter. And this is an example of an elastic collision. And I'm not sure just why they called it elastic. I think in this case, the word elastic was used well before elastic was used as a definition or as the name of some stretchy fabric. So that's how it worked. But an elastic collision means kinetic energy is conserved, which is not always the case in collisions. Now, most of the time when we think of a collision, we think of two things that smack into each other, and maybe there's some wreckage, some stuff like that. And the force that acts between the two objects is the electromagnetic force. And the atoms near the surface of one of the objects will push on the atoms near the surface or at the surface of the other object and deform that surface, putting dents in the two things, and both things come out of it with some damage. And those are usually what we consider collisions. But in this case, it's a collision where the force that's doing the interaction is the attractive force between Jupiter and this spacecraft. And that's the force that governs this collision. So the gravitational force can act in collisions as well. You can also have the electromagnetic force acting between collisions of elementary particles. But in this case, the gravitational force is actually a relatively gentle force, even though it's going to slingshot this spacecraft around here and send it on in that direction. But kinetic energy is conserved. And what that means is that the initial kinetic energy, which is going to be 1/2 the mass of Voyager times V initial for, I'll call it VIV and V final V, that thing squared, plus 1/2 the mass, the mass of Jupiter times V Jupiter initial squared. That's the initial kinetic energy. That will equal the, let's see, we'll have 1/2 the mass of Voyager, V Voyager final squared, plus 1/2 the mass of Jupiter, V Jupiter final squared. So there's a conservation of energy condition there. Now, we know the initial velocity of Voyager, we know the mass of Voyager, we know the mass of Jupiter, and we know the initial velocity of Jupiter, or the initial speed of Jupiter. So we know everything here. What we don't know are the final velocity of Voyager and the final velocity of Jupiter. Okay, well, it turns out this one is just about the same as what it started with. So Jupiter does not get slowed down much by an encounter with a, say, I don't know how much this thing, what its mass was. I seem to remember it was something like 750 kilograms. Okay, the mass of this is about 2 × 10⁻27 kilograms. So this wins the collision. It doesn't even notice it. But still, when you have only one equation, you cannot find two unknowns. And so we need another equation. And that other equation comes from the conservation of momentum. And momentum has direction. So I'm going to give direction to these things. I would say the initial momentum is going to equal the final. Well, if I say positive is to the right, then Jupiter has positive momentum to begin with. It's got the mass of Jupiter. Oh, and I just wrote Jupiter's mass with a capital M. Maybe I should, because it's bigger. Anyway, times V Jupiter initial. That's positive momentum minus the mass of Voyager, V initial for Voyager, will equal the mass of Jupiter, V Jupiter final. Voyager is going to be going in that direction after the collision, plus the mass of Voyager, V Voyager final. I think that's the letter I used. Yeah. So there's our conservation of momentum equation with direction taken into account. The only thing that comes out negative is this one. So we will have that. And you can solve this, and it turns out that the final speed of Voyager, which is what we care about, ends up being around 3 times its initial speed. And so it picks up a whole lot of energy. Its final kinetic energy is actually 9 times its initial kinetic energy, because if you triple something that gets squared in the kinetic energy calculation, it has that. And it was this encounter with Jupiter that gave one of the Voyager spacecraft enough energy to leave the solar system. The other Voyager spacecraft did this gravitational encounter at Jupiter, went by and visited Saturn, which gave it another gravitational slingshot effect, and it went by Uranus and just flew by that planet, took lots of pictures, measured things with instruments, and then it went by Neptune and did the same thing. But that's a place where conservation of momentum and energy was used, and it was an elastic collision where kinetic energy is conserved. And that's something that happens in those types of collisions. The actual analysis of this involves about half a page of algebra. It's actually not something that is impossible. In fact, if you've completed, whatever it is, Math 98 or 99, I lose track of the numbers. They've been renumbered since I taught them last. But if you can factor the difference of 2 squares, that's the hardest trick of math that there is in solving these things. And you can end up with an exact expression for the final speed of Voyager and for the final speed of Jupiter. Voyager ends up getting about triple its initial speed out of this. Jupiter ends up losing an amount of speed that would take it something like 1 billion years to be 1 meter farther behind in its orbit. And so it's not going to make any difference stealing that little bit of energy from Jupiter. But kind of a neat example anyway. All right, now we'll have an inelastic collision though. We have a car moving at 10 meters per second that crashes into a tree and stops in 0.26 seconds. Calculate the force the seat belt exerts on a passenger in the car to bring him to a fault, or to a halt. The mass of the passenger is 70 kilograms. See, if a car comes to a stop in a collision, you hope that the passengers do too. If the passengers don't come to a halt in the collision, that means they were thrown through the windshield of the car and they're now a projectile outside the car instead of a passenger in the car, and that's worse. So what would be the answer to this question be different if the car with the 70 kilogram passenger had collided with a car that had a mass equal to and traveling in the opposite direction and at the same speed? Well, if you've got two cars going in opposite directions with equal momenta and they crash, they're each going to stop in that case. If one of them has a little bit more momentum than the other one, then they'll end up going slightly in the direction of the car with the greater momentum. But most of the momentum is going to get lost in that situation because there was not that much momentum to start with, actually, because it has direction. But in this case, the tree stops the car. So all of the momentum is lost. And here's what's going to happen. The passenger receives an impulse from the seat belts of the car, or the seat belt of the car. And so we will have the change in momentum for the passenger. Delta P is going to equal 0 minus the passenger's mass, and I'll put a P subscript on there, times the initial velocity of that passenger. And that will be the impulse received, the I for impulse, which is equal to the average force exerted times the time interval during which that force is exerted. So during which the passenger is being brought to a halt, and we're told that this takes 0.26 seconds. So that's delta T in this case. Okay, well, I've got a minus sign in here. Looks like I made a choice that, well, I haven't made any choice yet, but I'll just assume that the direction the passenger and the car were going in initially is the positive direction. The force will end up being negative, and that just tells me that it is opposite the initial direction of the passenger. So that's okay, I can live with that. So basically I have these two things being equal to each other. So minus the 70 kilogram passenger, and the initial speed was just 10 meters per second. That's my minus MPVIP, and that's going to equal that average force times the time during which it acted, 0.26 seconds. So the average force ends up being, does it ask for the magnitude? Nope, just says force. I'll have a minus sign on it, doesn't bother me. 70 times 10 divided by 0.26. Which is 2.7, actually 1 sig fig, 1 sig fig, 2 sig figs. So I'm just going to call it minus 3,000 newtons. I get about 2,700 newtons, but for 1 sig fig, minus 3,000 newtons is all that I have there, which isn't a nice force to have acting on you. If I divide that by, it's about a 600-pound force acting on you to stop you moving, but it's better than going through the windshield. And so you might have bruises from the seat belt or the shoulder strap in a collision like that. And actually, yeah, running into a tree is a pretty violent collision to experience. So, but again, this time change in momentum. The object was brought to 0. That requires an impulse, which is an average force acting for some time. So more stuff. Oh, I'm going to write this as 9.00 times 10 squared kilograms. So that we've got 3 sig figs, 3 sig figs, only 2 sig figs there, and 12 or 3 sig figs here. I'll write this as 1.50 times 10 squared kilogram deer. So we have 3 significant figures all around. And here's what we have in this case. The car is going down the road at 30 meters per second, a little over 60 miles an hour. Just after it hits a it was initially moving at that speed, it hits a 150 kilogram deer initially running at 12 meters per second in the same direction. Assume the deer remains on the car. So here's what we have. Before the collision, you've got the car headed down the road here, and it's going at 30.0 meters per second. And then there's a deer running down the road here. I don't know. And it's got antlers or something like that. It's going at 12 meters per second. And so after the collision, we have the car going down the road here with some final velocity. And the deer is laid over the front of the car. And so I'll put X's up there instead of I's, I guess. So anyway, that's the final situation. And there'll be some V final here that we don't know. Okay. Well, let's see how this works out. Before, our initial momentum is going to equal our final momentum. Everything's going to the right, so it's all positive this time. I'll have the mass of the car times 30.0 meters per second plus the mass of the deer. I could have called these V car initial and V deer initial, but I'll just punch in the numbers here. And that will equal this final situation here. We've got the car and the deer attached to each other, more or less. The deer's laying on the hood. I'll have the mass of the car plus the mass of the deer times V final. So if I solve for V final, it will equal, the mass of the car is 900 kilograms times 30.0 meters per second plus the mass of the deer, which is 150 kilograms, times the 12 meters per second. And I'll divide by the mass of the car plus that of the deer, which will bring this 900 plus 150 is 1,050 kilograms. And that'll be the final velocity. Then we can figure out what that is. Again, the mathematics isn't hard, but you have to realize that the initial momentum equals the final momentum and be able to express both of those things in terms of what we have. So the hardest part on this is to wrap the numerator in parentheses. So 900 times 30 plus 150 times 12 in parenthesis divided by 1,050. And I get about, actually the final is 27.4 meters per second. So the car slowed down a little bit. It was going 30 miles an hour, which is, maybe 30 meters per second, which is about 66 miles an hour. Afterwards, it's going about that fast, which is closer to 60 miles an hour. So, but it loses a little bit of speed there, and you can bet the guy's going to hit the brakes shortly after that collision because there's a severely wounded deer right in front of him on the hood. So that's what would happen in this case. Okay, I hope after a while. Yeah, we'll start elastic and take a look at some elastic collisions tomorrow. And do things with that. Okay, that's about enough for today. Oh, I'm going to try to put up some practice problems for the final.
I have a question about the sapling assignment. So there's, I think at the end of it, there's a block of about 3 questions, and they're all like 2-dimensional stuff. Are we going to be covering 2-dimensional momentum at some point?
Yeah, I can show you how those things work out. I think they're set up in such a way that at least 1 or 2 of them, the 2 objects are moving perpendicular to each other before the collision, if I remember right. And they stick together after the collision, don't they? Isn't it like a hawk capturing a dove or something?
Yeah.
Or, you know, some pigeon, I don't remember. But anyway, you're basically adding 2 vectors together is what you're doing. You think of the initial momentum of one of them as a vector because it's got a magnitude and direction, and the initial momentum of the other as a vector. And then you're adding those 2 vectors together. So,
Okay.
but we can do one of those tomorrow, or one like that anyway, to see how they work out. Yeah, and for some reason, those problems were before the collisions of point masses in 2 dimensions. They were before that section. I was a little surprised by that, but yeah, we can take a look at those tomorrow. Okay, man, I've got a scratchy voice today. I think my allergy medicine is not working. There's something blooming that it's not touching, but I will see you tomorrow, I think. And again, I'll try to post some practice problems for the final. Probably reuse the ones from for the Unit 1 test and the Unit 2 tests, and then I'll just introduce some more for this latest unit.